Okay, then I would say we start with the second Python package for today. Again, it's going to be a relatively short one, and that is networkx. So basic Python library for network analysis is not just used for power systems or power networks, but can be used for many different things from routing, uh, and navigation to kind of relations in social media or anything that can be represented as a network. And again, it just provides some formal data structure for graphs in Python, and then functionality to run many of the standard graph algorithms, such as finding the shortest path through a network, clustering networks, finding cycles that we need for the power flow linearization that we talked about last week, and many more functionalities. What our initial goal would be is to build a representation of this simple graph, kind of 5 nodes, and not everything is connected. And of course, if we wanted to calculate some metric of the graph, for example, the so-called Laplacian that you can calculate from the incidence matrix. If you don't know what the Laplacian is, it's absolutely no problem. You know, it's just some calculation that we can do based on the incidence matrix of a network graph. Of course, we could do all of that in form of NumPy. After all these things like the incidence matrix or the adjacency matrix as well that we briefly talked about last week, they are matrices. Matrices are 2D arrays, and we could just write up everything in a NumPy array. Kind of the first line starts at node 1, ends at node 2. The second line starts at node 1, ends at node 3, and so on. So we could just build our incidence matrix and do this calculation of the Laplacian. Fair enough. So you might ask, okay, why do I then need something else? And well, you can imagine for a larger network, this might become a little bit too tedious to handle, and we also want access to this general functionality, these functionalities like calculating the shortest graph and so on, and we don't necessarily want to re-implement all the logic based on our NumPy objects ourselves. So here comes networkx, which we typically import under the name nx. And again, it comes with the basic data structure. An empty graph you can create with a graph constructor, and we could name that, for example, G for our graph. Elements of the graph, you know from last time, we have basically nodes and edges. In terms of power systems, we would often say buses and lines. And there's functionality to add these nodes one by one. We could add a node called 1. We could add a node called 2 with an arbitrary attribute, for example, country DE. And of course, we don't have to add them one by one. We could also add nodes from a list. So we could add nodes 3 and 4 with a single call to the graph object. What we can also do is when we want to add multiple nodes at one point in time, but each with attributes, we can pass the attributes in this slightly complicated structure where we pass a list of nodes, but each node basically consists of a tuple of a name and a dictionary of attributes. The edges we can add basically in a similar way. The syntax is almost exactly the same, other than adding nodes, we add edges. And here we specify the connection between nodes. So we say this edge should go from 1, or should be between 1 and 2. Another edge should be between 3 and 4. And again, we can assign them arbitrary attributes, for example, a weight. We can add a list of edges, and here again we have kind of this nested structure where we pass a list of pairs of starting and end nodes. So we have one edge from 1 to 3 and another edge from 2 to 5. And if we need here as well some attributes such as the weight, we would have not 2 elements in the tuple, but 3 elements in the tuple, and the third one would be just the dictionary with the weights. So we have now a simple graph. It's actually the graph that you saw at the beginning, with g.nodes, which lets us inspect the nodes of the system. We have 1 to 6 nodes. There's also a function number of nodes, which tells you the number of nodes. I think at least this is how it used to be. You can also use the len function, which gives you the length of the nodes. And of course, the same for the edges. So you get this attribute component, which just lists you all the edges in the system. In pandas, for example, one important element was accessing particular components of a data frame. And this is also possible in graphs. We can use, again, square brackets to access individual elements. For example, the edge that goes from 2 to 3, and that would give us the attributes of that edge. Here we used weights as attributes. And this is just a dictionary so that we can also just access this value. So this g edges to 3, it will just return a dictionary that we can work with like any other dictionary in Python. If we just do this notation, g square brackets 1, it gives you basically all the neighbors of this node. So it doesn't explicitly list you the edges that are connected to it or something like that, or the attributes of the node itself, but it lists you just the neighbors. And node 1 in this case is connected to nodes 2 and 3. So when there's a function for adding things, there's also a function for removing things. We can remove node 5, and we can also try to remove things that don't exist. And in this case, we will get an error. networkx will say the edge 2 to 5 is not in the graph, so why do you try to remove it? Again, good example of how you can read error messages from the bottom to the top. You can this will be most insightful and give you an idea of the characteristic of the error, and then you can scroll up and find out in which line this error occurred. In this case, we only had one line, so it was not really a question, but if you had here 20 or 100 different lines, you would kind of use this to easily find where the error occurred. So one note here is that if you decide to remove a node in the graph, automatically all the edges that are connected to it are also removed. Okay, sometimes it can be useful to draw a graph or to visualize a graph, and there's a draw function in networkx that lets you do that. Just takes the graph as an input, and it produces you a plot that is also based on matplotlib. So this doesn't give you a lot of information. For example, it doesn't give you any labels, but there's also a keyword argument here with labels, which you can set to true, and then your nodes will be labeled. And you can combine this with matplotlib by, for example, first creating a matplotlib figure, and then kind of constructing the same command as before for networkx draw, and passing the axis onto which you want to plot. And then you also have various style options, like specifying the node color or the font weight. And then in this way, you can control how these plots are portrayed. And if you need more functionality, then you can just follow this link, which gives you all the configuration options. Okay, plotting and accessing elements doesn't help us help us too much yet, but in many cases we want to analyze the graphs that we are studying, for example calculating things like the incidence matrix or the cycles in a network to then use them in power flow calculations. One thing we can check, for example, whether the network is connected. That means just whether all of the nodes in a network are reachable from every other node. In this case, we have this isolated node 6. So NX is connected returns false. And we can also figure out what the components are that are connected by running this connected components function, which will split our network into the nodes that are connected among each other. And that also just illustrates how the node 6 is isolated from the rest of the network. In terms of power systems, this could be useful, for example, to isolate separate synchronous zones. For example, you would have an isolated network for Iceland. You would have, at least in alternating current, an isolated network for the British Isles, and an isolated network, for example, for the Nordics, and it used to be like this until earlier this year or last year, that the Baltic system was its own, or was not connected to the main synchronous zone in continental Europe. There are various other things, like whether the network is planar, which means that the lines are not crossing each other. And you can look at the frequency of the degrees in the network. And remember, the degree of a network or the degree of a bus just tells you how well connected a node is. So how many transmission lines, for example, in the context of power system, is it connected to? And this function degree histogram will give you this list, 1, 1, 2, 1. What does it mean? Well, it means that there's one node that is connected to no other node. There's one node that is connected to one other node. And there are two nodes that are connected to two nodes. And there's one that is connected to three nodes. It becomes easier to see if we wrap it into a pandas series, where the index would just give you the degree, and the values here would just count how often this degree occurs in the network. There are simple functions for creating the adjacency and the incidence matrix. One thing one has to be careful about is that networkx by default says that the incidence matrix is not oriented, meaning that it assumes it assumes no direction of the transmission lines, or not necessarily transmission lines, of the edges between the nodes. But for example, when we do a counting of the power flows, even though there's not a clear kind of one-way direction of the flows, because the power flows could in principle also go the other way around. for the accounting, how we put it into the energy balances, we need to decide whether a positive value of the flows represents flows in one direction or whether it represents flows in the other direction. So we need for these incidence matrix some orientation, meaning that one end would have a value of -1 and the other end would have a value of 1. So that if you think now about the Kirchhoff's current law, the energy balances, you would have the flow of one node being extracted, extracted from one of the node and injected into the other node that it is connected, so that you have so every transmission line doesn't magically create energy, but it takes power from one node and brings it to another node. It's also, in fact, a function for the Laplacian, which would give us exactly the same values that we calculated at the beginning. There's one more function that is useful for these Kirchhoff voltage laws, and that is calculating the cycles in the network, where Kirchhoff voltage law tells you that the voltage angle differences around any cycle in the network need to add up to 0. And in fact, you don't really need all the possible cycles in a network, but just a so-called cycle basis. So this would be a set of linearly independent cycles through which you can construct all the other cycles. And in this case, if you scroll up, we have one cycle in this network between 1, 2, and 3. And this is how network X returns the cycles as a sequence of nodes that are traversed. So let's do an example. Slightly bigger data set. I brought a slightly outdated data set of the European transmission network. We have here one data set of buses, where we just have the bus ID and the X and Y coordinates. And then we have one more data set for the edges, where you have the line IDs, the bus 0, so the first bus it's connected to, and the second bus it's connected to, bus 1, as well as two attributes. The S num would be the nominal power in megawatts, and the X per unit, so XPU would be the per unit reactance of the line. So remember this X, this is part of the Kirchhoff voltage law equations that we were using in combination with the cycles. And then the S num would be just the limits of the power flows on the lines. So in this case, there's actually some nice functionality that lets you construct a network from a pandas edge list. So in fact, we're actually not right now using this nodes dataset at all, but we're just using this function from pandas edge list. We'll give the edges, we give the columns that represent the start and the end columns, the start and the end of the lines, and then have the rest as edge attributes. So as attributes of the lines. And we store this under the name n. And if we print the n, we get this small representation. This is a graph with 3,500 nodes and 5,000 edges. And we can run the same functions that we looked at earlier. For example, this degree histogram, and plot this as a histogram, where we just have on the x-axis then the number of connections, and we find that kind of more than 1,600 nodes have exactly two connections to other nodes. And that, for example, there are very few nodes that are connected to just one other node. These would be kind of endpoints in the network. And there are also very few nodes that have kind of very many connections of 8, 9, 10, or 11 nodes. We can also calculate the average degree. So on average, in this European data set, we would have three lines, or three, we would have the case that every node on average is connected to three other nodes. For the drawing, we can bring in the coordinates of the nodes, but we have to put them in a particular format in this style, a dictionary with the nodes as a key and then the tuples of the x and y coordinates as tuples. So it's a bit of a peculiar layout, but this is a line of code that prepares the flow in this way. So we have exactly that we have the bus ID as index and then the x and y coordinates as tuples, which we can pass into, yeah, that would have been the clever solution, that we can now pass into the nx draw function. So we have our graph n, and in addition, we provide the pos keyword argument, which is in this format, and plot this, and we get kind of clearly a European picture out of that, even without kind of plotting the surrounding coastlines, for example. So you can also, so there's one thing that this data set doesn't have that exists in power systems in reality. These edges I added here, they are only the HVAC lines, so the alternating high voltage alternating current lines. And we have here different isolated systems, the Great Britain, we have Ireland. In this data set is a bit older, so we have the Baltic isolated and then the Nordics isolated. Mallorca is also islanded here. So we have actually several different disconnected systems. It's because the HVDC, so the high voltage direct current lines, are not represented in this data set for illustrative purposes. So what it looks like now in reality is that you have these four main synchronous zones in Europe, the island of Ireland, Great Britain, Nordics, continental Europe, and some of the islands also are their own synchronous systems, but they're not shown here on this graph. So can we actually, color this graph in a way that we see the disconnected areas? Let's try that. So we can use again this function connected components, which tells us that there are 7 disconnected systems. And we can actually iterate over the elements in the connected components. If you remember, the NX connected components of the simple graph, G, would be something like a list of nodes that are part of a subnetwork. So we can iterate over each item in this list, and these would represent then the subgraphs of the network. And we know there are 7 of them, and we can build these subgraphs by using this function subgraph, which takes a selection of nodes of the original graph and makes a copy of the kind of subset of the network that is connected to these nodes. And we can do this for every one of these interconnected, not connected components, and then kind of give a color for each of the 7 nodes and kind of iterate over the subgraphs and plot each of them, but each of them with a different color. And that would tell us then quickly kind of what are the systems that are not connected within each other, but not connected to the other parts of the network. In this case, it's more or less obvious that because there's a clear geographical separation, But in principle, it could also be that there are, yeah, not in Europe, but in principle, it could also be that here they're actually not geographically separated um, kind of converters, back-to-back converters that make the system not synchronous, not connected by HVAC lines. In this case, we don't have that, so this coloring here just confirms what we saw previously already visually. So I'll stop here for the for this tutorial. There are a couple of exercises here where you can kind of build another small network and get familiarize yourself with the functionality. But I would say we take another, maybe this time, 15-minute break, and then continue with the lecture on optimization in electricity markets.